Okay, so I want to take a look at this thing. You might remember how to divide polynomials, but if you don't, I'm going to run through this example, and then at the end, we're going to do some new stuff with it. So you should have been dividing the polynomials back in Algebra 2, um, but I'm going to take it a step further after we divide the polynomials. So the first thing I want to do, instead of this polynomial problem that's sitting right in front of us, I want to do this problem, which is like 4th grade. So it's 49,205 divided by 8, but I want to do it using long division. So this is my side example. So using long division, remember we put the numerator on the inside of that division symbol. 8 goes here, and then I have to figure out, well, how many times does 8 go into 4? None. So then I look at the 49 and I say, well, it goes in 6 times, and 6 times 8 is 48, and I subtract. And then I bring down the 2. And so now I repeat the process. So how many times does 8 go into 12? 1 time. So I put the 8 here, and I subtract. And then I bring down the 0. And, you know, I've got 5 8s going to 40, and it goes in perfectly. So I get 0 left over here. And then I have the 5 left over at the end, and 0 times 8 goes into 5, so 0 goes here, I subtract, I still have 5. And then you guys have learned some different terms for these things, but usually people call 8 the divisor. You probably remember that this is called the remainder. And then this up here, the actual main answer is the quotient. And so the way that I want to write that original fraction is, you guys probably got used to writing R5, but I don't want to write R5. Instead, I want to rewrite my fraction 49,205 over 8. If it was 49,200, then it would have been exactly 6150. But I've got that extra 5 over 8 left over, so I'm going to write it like this, plus 5 over 8. And so what I want you to notice here is that my original problem I'm writing as the quotient plus, quotient plus the remainder over the divisor. And notice here the remainder has to be less than the divisor, because if it was like 9 over 8, well, then you should have divided that extra 1 out, and you would have gotten 6151 plus 1/8, right? So notice that this has to be smaller. The numerator, the remainder, has to be less than the divisor. That's kind of a key idea I'm going to come back to. So now let's do this long division problem in example 1, which is significantly uglier looking. And we're going to kind of run through a very similar process. So it's going to be 3x to the 5th. The numerator goes on the inside of this thing. 2x to the 4th. There's a nice trick here. Since there's no x cubes here, I'm going to pretend that there's a 0x cubed that I'm adding in, because that doesn't really change the value, but it gives me this nice placeholder for where x cubed terms would go. Minus 4x squared, and then there's a 0x plus 1. And then over here I've got x cubed, my divisor here, x cubed, plus 0x squared minus 2x plus 3. Okay, so numerator on the inside, denominator on the outside, or the divisor on the outside. And then the first term that I'm going to put right here, I'm going to ask what times x cubed is going to give me 3x to the 5th. And so that answer is going to be 3x squared. Because if I multiply 3x squared times x cubed, I get 3x to the 5th. And then just like over here where I was doing 6 times 8 is 48, I'm doing 3x squared times the entire thing here. So 3x squared times x cubed is that, plus 3x squared times 0x squared is 0x to the 4th, and then minus 6x cubed, and then plus 9x squared. And then just like I subtracted the 48 over here, I'm going to subtract this entire line from the line above it. The mistake students make, they always subtract the first 2 terms, and then for some reason they start adding. Just remember that minus distributes to everything here. So it's 3x to the 5th minus 3x to the 5th, those go away. 2x to the 4th minus 0x to the 4th is 2x to the 4th. 0 minus negative 6 is really a positive 6 x cubed. And negative 4 minus positive 9x squared will be negative 13x squared. So just keep that in mind. Now I'm going to bring down the 0x, just like I did over here where I brought down the 2. Okay, so I repeat the process. So what times x cubed is going to give me 2x to the 4th? So that's going to be a 2x. So if I do 2x times x cubed, I get 2x to the 4th. 2x times 0x squared is going to be 0x cubed. 2x times negative 2x is negative 4x squared. And 2x times 3 is plus 6x. And once again, I'm going to subtract that line out. So these cancel. 6 minus 0 is 6. Negative 13 minus negative 4 is really plus 4, so it becomes negative 9x squared. 0 minus 6x is negative 6x. And now I'm going to bring down my 1, plus 1. And then I'm going to do the process one more time. So what times x cubed gives me 6x cubed? Well, it's 6. And then if I work this out, I get 6x cubed plus 0x squared minus 12x plus 18. And then if I subtract, 6 minus 6 is 0. Negative 9 minus 0 is negative 9x squared. Negative 6 plus 12x, because of the negative. So that's a positive 6x. And then 1 minus 18 is negative 17. And at this point, that's my remainder now. So I can rewrite this original expression right here. So it's 3x to the 5th. This is the original. Minus 4x squared plus 1 over the x cubed minus 2x plus 3. I can write it just like I wrote over here, quotient plus remainder over divisor. So the quotient was this part, that's my quotient, 3x squared plus 2x plus 6, plus the remainder, this is my remainder, negative 9x squared plus 6x minus 17, over my divisor, which is x cubed minus 2x plus 3. And you remember how I said over here, notice the remainder is less than the divisor? Well, the way that shows up in this problem is the degree of the numerator, the degree of the remainder is always less than the degree of the denominator, of the divisor. Okay? So this right here, let me highlight this. This right here is a pretty important thing, the quotient. Quotient, Q of x, I'll call it. And then the remainder here, remainder, we'll call it r of x, and the divisor, we'll call that d of x. And remember, degree of r has to be less than the degree of d. Otherwise, you haven't actually finished the division problem, or you made a mistake somewhere. What I want to show you now, and I did this in class for those of you that were absent, was I showed a website that I've talked about a couple of times, wolframalpha.com. So I'm going to go to that right here. So let's go up here, wolframalpha.com. Hopefully this will work. There it is. And I'm going to type in the original problem. Now the original problem was to divide 3x to the 5th, let's see, plus 2x to the 4th, minus 4x squared plus 1 divided by x to the 3rd minus 2x plus 3. If I hit enter, Wolfram Alpha will actually calculate this stuff for you. It'll show you way more than you probably want for any one problem. And you just kind of have to piece through it. So if you look here, it gives you two graphs. This one is sort of zoomed out. It goes from negative 10 to 40, but it's actually zoomed in along the x. And then this one down here is much more zoomed out. If you notice, negative 500 all the way to 1,000, negative 15 to 15 for the x's. But if I scroll down a little bit more, notice here it says quotient and remainder. And there in the box is our quotient that we found, right? 3x squared plus 2x plus 6. And right on top here, or right up here, is the remainder that we found. And that is over here, negative 9x squared plus 6x plus 17. Now, if you actually click on step-by-step solution, it will show you all of the work right there, including the placeholders, right, the zeros. So that's convenient. That's kind of a nice little way of checking. You're still going to need to know how to do it by hand, so just make sure you actually take the time to practice. I realize that showing you this means you can just come here when you do your homework, but I expect you to still know how to do it by hand. So, one other thing I want to talk about here is this function right here. Like if you actually zoom out a lot, you might notice it looks an awful lot like a parabola, right? And in fact, that is a parabola, and it's a well, it looks like a particular parabola, but it's not x squared. It turns out that that parabola is the quotient right here. So let me do this. I will cut out this picture here, edit, copy, and I'll put it over here. Edit, paste. So there's my picture. Whoop. Right. And it looks an awful lot like the parabola, and it turns out that the parabola, it looks more and more like, as you zoom out, let me get a good color here. This parabola that it looks an awful lot like is the quotient. This is y equals 3x squared plus 2x plus 6. That's not the full function. Notice there's a vertical asymptote in the actual function. That's when the denominator up here was 0. When this is 0, that's when you get a vertical asymptote or a removable discontinuity. This one doesn't cancel, so it's the vertical asymptote, and this is when it happens. So the nice thing is Wolfram alpha can tell you what that asymptote is too. So if I go back to Wolfram alpha and scroll up, right here, I'm just going to leave that problem there, but in front I'm going to type the word asymptote. So we'll give it a second. And here it is. Notice it says vertical asymptote near x equals about -2. If you scroll down, there's that vertical asymptote right there. That happens when that denominator is 0. The other thing you notice is there's this dotted parabola here. It's not a horizontal asymptote. It's a parabolic asymptote instead. So it says that it tells us that it's asymptotic to this quadratic that we found. That was our quotient, right? So my question is, why does it have a parabolic asymptote? And why does it start to look like this parabola way out at the ends? So let's go back to the division problem, right? So let's see here. Here's the answer that we got, right? Let me scroll back over here. So in the problem that we did, we rewrote it right here, right? That's the problem we rewrote. And if you think about what happens, the asymptotes, the end behavior asymptotes tell you what the graph looks like way out at the ends of the graph. Doesn't matter about the middle. So this part of the graph I don't really care about. I just care about way out here or actually let me do this. I care about the x values that are way over here and the x values that are way over here, which means I care about when x is going to infinity or when x is going to -infinity. So if you look at this term right here, because that's the term that sort of disappears when we're talking about that parabolic asymptote, this term right here, if I think about what happens as I go to infinity or I go to -infinity, since I'm taking infinite limits here, I don't have to examine the entire function. I can just look at the dominant terms. -9x squared over x cubed, -9x squared over x cubed. And these, right, well, the only place that this gets messed up is at 0. So way out at infinity, this thing looks pretty much like this, -9 over x, if I cancel out the x squareds. And then this is going to do the same thing, except -infinity, -9 over x. Well, think about this. This is going to turn into 0, and this is going to turn into 0. So that's saying that this whole term right here, way out at infinity, turns into 0. And at -infinity, it turns into 0. So way out at the ends of the graph, way out over here and over here, The only thing that really plays a role is this parabola. This part of the equation takes over way out at infinity because this thing disappears or becomes less and less significant because it just keeps getting closer and closer and closer to zero. Okay? So we actually don't get a horizontal asymptote in this case. The quotient will always tell you what sort of asymptote you get way out at the ends of a rational function. And in this case, it happens to be a parabola. If I had given you some problem that looked like this, let's look at this function. F of x equals 3x to the 7th minus 4x cubed plus whatever, at smaller terms, let's say, plus 3 at the end. And I was dividing it by 2x to the 6th plus, and then terms that were smaller than that, down to a constant. Well, I'm not going to work out the whole problem, but you can say pretty quickly, when I do this division problem, if I were to do long division, the first and the biggest term I would get in my quotient would be 3 over 2x plus some constant plus the remainder over the divisor. Well, the remainder over the divisor is always going to turn into 0 way out at infinity, and I'm going to get some sort of linear equation for my asymptote, for the end behavior asymptote. So that means that whatever this graph looks like, way out at the ends, I'm going to get some line that's like y equals 3 over 2x plus some number, like let's say it's 1, right? And I don't know what else is going to be messed up in the graph. Let's say there's a vertical asymptote here and a vertical asymptote there. What I do know is way out at the ends of the graph, it's going to look an awful lot like this line. And, I don't know exactly what it looks like. Maybe it does some weird thing like this. But way out at the ends, it's going to look like the line that I found here in the quotient. Right? The quotient always tells you the end behavior asymptote. It'll even tell you if it's horizontal or not. If you got 4 plus remainder over divisor, then y equals 4 is going to be your horizontal asymptote. So there are different types that you can get. If it's a curved asymptote, like a parabola, if it's a curved one, then they all go in the category called curvilinear asymptotes. If it is a straight asymptote, a linear one, but it's slanted like this, then, so slanted but linear, then we would call it instead a slant or an oblique asymptote. And then there's one other type, and those are the ones that we've already studied, horizontal asymptotes too. So there are 3 main types here that we're going to look at: curvilinear, slant or oblique, and horizontal asymptotes. And so if you always do the division, it's always going to be the quotient. These are your 3 types of end behavior asymptotes. Remember, those are different from vertical asymptotes, which don't tell you end behavior. Okay, so there we go. If you watch the next video on synthetic division, I'll basically talk a little bit more about this, but the main idea of the other video is practicing the synthetic division. So, okay, hope this helps.